Now, to actually analyze the motion of a pendulum in complete detail, to get everything exactly right, we would have to use techniques that even the university physics class can't use. We'd need to use the techniques of differential equations, a course usually taken in the 4th semester of a calculus sequence. So obviously we're not going to do that here. So both in an introductory physics course, a non-calculus based, even a calculus based physics course, we make the small angle approximation. Now in the higher level course we get a little more technical, but it comes down to this. The small angle approximation comes down to this. We assume that the angle of the pendulum with vertical is so small that the y component of the tension is not significantly different in magnitude from the entire tension. So we say that the y component of the tension is mg, which means that the y component of the tension balances the downward force of gravity. Now that obviously isn't quite true, because if it was, we wouldn't need the tension to be out in this direction, and if the tension isn't out in this direction, we have no force component in this direction, so the pendulum doesn't swing. But this is our small angle approximation. It doesn't make a lot of difference for small angles. Now, we've got a pendulum here depicting a 30-degree angle from vertical, and that's not really a small angle. The small angle approximation isn't really great at 30 degrees, but at 5 degrees, 10 degrees, it's pretty good. Okay, well, then the y component of the tension is going to be equal in magnitude to the weight of the pendulum, to mg, m being the mass of the pendulum. And the tension itself is equal to mg. Again, that can't really be so. They can't really both be equal to mg, but they differ by so little that we make this approximation. In that case, since at a 30-degree angle, again, a 30-degree angle is not a real good example of a small angle, but at a 30-degree angle, the tension vector here is at 120 degrees, at least the way I've drawn it here. The vector is back in this direction. Well, there it is, parallel to the string, pulling back on the mass. And if this is 30 degrees, if the angle here is 30 degrees with vertical, then if we measure the angle from the positive x-axis in the counterclockwise direction, we have 90 degrees from here to here, and another 30 from here to here, making 120 degrees. So the angle of that vector is 120 degrees. This means that the x component of the tension is the magnitude of the tension multiplied by the cosine of 120 degrees. The magnitude of the tension is what? It's mg. So that's mg times the cosine of 120 degrees. And cosine of 120 degrees is negative 1/2 or negative 0.5. So that's negative 0.5 times mg, which is negative 1/2 mg. Now, since the y component of the tension is equal and opposite to mg, the y component of the tension and mg add up to 0. The x component of the tension is all that's left. And we can draw a little curvy thing, a little curvy hook or something through this tension vector to indicate that we're replacing the tension vector with its ty and tx components. Having done that, the ty and the mg add up to 0, equal and opposite, and the tx is what's left, and it's the tx that pulls us back toward equilibrium, and that's what makes the pendulum swing back.